If you place a block on a perfectly frictionless plane and apply a lateral force, it accelerates immediately, following Newton's second law. But in the physical world, surfaces have microscopic roughness. Apply that same initial force to a real block, and it remains static. It stays in place because of dry, or Coulomb friction. This is a self-adjusting reactive force. As you push harder, the friction force increases to perfectly match your applied load, maintaining static equilibrium. There is a precise physical threshold where this equilibrium breaks. We call this limiting friction, the exact moment where the reactive force maxes out and relative motion is about to begin. Coulomb's laws dictate how this threshold behaves. The force always opposes impending motion, operates independently of surface area, and is determined by material roughness. Mathematically, this limiting threshold means the maximum friction force is strictly proportional to the normal force pressing the surfaces together. This ratio is defined by the coefficient of friction, represented by the Greek letter mu. Translating this scalar limit into a geometric angle allows for the analysis of advanced mechanical systems without relying on coordinate-heavy algebra. Look at this diagram. At the exact moment of impending motion, we plot the forces on this block using orthogonal components: a downward vector for weight, an upward vector for normal force, and a horizontal vector opposing the push for limiting friction. We can simplify this. Using vector addition, we merge the normal and frictional forces into a single diagonal resultant vector. This new vector creates a specific angle relative to the normal axis. This is the angle of friction, denoted as alpha. The tangent of alpha is exactly equal to the coefficient of friction, mu. We can observe this same property by inclining the resting surface. If we increase the tilt until gravity alone forces the block to the verge of slipping, we find another critical threshold. We call this the angle of repose. Because the tangent of the angle of repose also equals the coefficient of friction, the math resolves perfectly. The angle of repose and the angle of friction are identical. We can take this two-dimensional resultant vector and translate it into a 3D spatial boundary by sweeping it a full 360 degrees around the normal axis. This generates an inverted right circular cone. The geometry of this cone dictates the stability of the system. If the resultant force vector remains inside the volume of the cone, the system is perfectly stable. If the resultant force pushes outward and touches the exact boundary of the cone, the system enters a state of impending motion. The cone of friction shifts the engineering problem. Instead of balancing multiple algebraic equations, you only need to ensure your force vector stays within this defined spatial domain of stability. This spatial logic scales directly to complex industrial environments. In workshops like this, engineers frequently use wedges to lift heavy machinery or split components apart. When modeling forces to drive a wedge, engineers fall into an analytical trap, treating friction on every contact surface as an independent calculation. Using this traditional Cartesian approach, we plot the normal and frictional components separately. We do this for the floor, the vertical wall, and the inclined surface of the wedge itself. Because each surface requires x and y equations, this method creates a gridlock of simultaneous equations, highly prone to calculation errors. We can bypass this by applying our angle of friction. If we delete the orthogonal components entirely, we can replace them with single resultant factors, each offset by the angle of friction from its normal plane. Now, if we isolate the wedge from the surrounding environment, the complexity of the force state disappears. We are left with the horizontal pushing force and two resultant vectors. Because these three vectors intersect at a single unified point, we now have a system of three concurrent forces in equilibrium. This allows us to apply Lami's theorem. We simply relate the magnitude of each force to the sine of the angle directly opposite it. Bypassing Cartesian coordinates for geometric resultants reduces the mathematical burden of wedge analysis to a single trigonometric relationship. Lami's theorem only works when forces meet at a single point. If we analyze a ladder leaning against a wall, that rule breaks down. Looking at this diagram, we map the downward weight of the ladder and the climber, plus the normal and frictional reactions at both the floor and the wall. If we extend the lines of action for all these vectors, they cross each other in multiple places. They do not converge at a single point. Because these forces are non-concurrent, establishing translational equilibrium along the x and y axes is no longer sufficient to determine when the ladder will slip. We have to introduce rotational equilibrium. By setting a pivot point at the base, we calculate the sum of the moments, balancing the downward clockwise torque against the upward counterclockwise torque from the wall. As the climber moves up the ladder, their changing position shifts the rotational balance. This dynamically alters the normal forces at the contact points, pushing the system towards its frictional limits at the floor and wall simultaneously. For non-concurrent geometry, the threshold of failure is governed just as much by torque and rotational pivot points as it is by the raw friction vectors. In this system, friction operates along the entire contact arc where the rope meets the wooden cylinder. When a rope is wrapped around a fixed drum like this to hold a load, the friction between the rope and the wood creates a massive difference between the tension on the tight side holding the weight and the effort required on the slack side. To model this mathematically, we look at this 2D diagram and isolate an infinitely small slice of the rope along the curve, labeled d theta. The tension on one side is T, and on the other, it's slightly higher, T plus dt. Within this tiny arc, the inward pole of the tension is balanced by an outward radial normal force. Along the tangent of the arc, the friction force perfectly opposes the slip. As tension moves from the slack side toward the tight side, the incremental friction at every point is proportional to the tension already present at that specific spot on the curve. Integrating this relationship across the entire contact angle shows that the tension doesn't just add up, it compounds as it sweeps around the cylinder. This compounding effect results in a nonlinear scaling of resistance. The holding force follows an exponential curve defined by Euler's number, where the coefficient of friction and the contact angle sit in the exponent. For this exponent to function mathematically, the contact angle theta must strictly be measured in radians, not degrees. This exponential accumulation allows a small physical effort on a slack rope to arrest massive industrial loads in band brakes in windlasses. Friction is a highly specific mathematical boundary that changes based on its geometric context. On a flat plane, friction dictates a three-dimensional cone of stability that contains our physical force vectors. In multi-body concurrent systems, the angle of friction provides a vector shortcut to bypass gridlocked algebra. And when applied over continuous curves, friction sheds its linear limits and scales exponentially to provide massive mechanical leverage. Mastering the mathematics of dry friction requires translating reactive physical constraints into precise geometric models. It provides the invisible scaffolding that makes structural and mechanical design possible. If you hit a tree stump with a sledgehammer, you'll just dent the wood. But if you drive a small metal wedge into that same stump, you redirect the horizontal impact outward, splitting the solid grain completely in half. Wedges are one of the oldest simple machines we have, acting as a force multiplier to turn a small input into a massive vertical lift. This diagram shows exactly how that lift operates. We have a 1,500 Newton block resting against a vertical wall, and our goal is to calculate the precise horizontal force required to drive a 10-degree wedge underneath it. Because these surfaces aren't perfectly smooth, the wedge has to overcome friction at every single contact point. We are looking for the exact moment of impending motion, the split second before the block actually slides. At this threshold, friction reaches its absolute limit, which we calculate by multiplying the normal force by the coefficient of friction, mu. To find the minimum effort required to push this wedge, we must analyze the entire mechanical system frozen right at this boundary of maximum friction. When you map out the individual forces for this setup, the free body diagram gets messy quickly. We have three separate contact surfaces: the floor, the wall, and the inclined wedge face. Each surface generates its own perpendicular normal force and its own parallel friction force. That gives us 6 separate unknown variables to track. Trying to balance all of these simultaneously in standard equilibrium equations is the primary cause of calculation errors. We can clean this up. Instead of treating the normal and friction forces as 2 separate vectors, we combine them. Because they sit at right angles to each other, they merge into a single diagonal resultant vector, which we'll call R. This resultant force is tilted slightly away from the normal line. We determine the exact degree of that tilt, known as the angle of friction, by taking the inverse tangent of our friction coefficient. For this system, our coefficient of friction is 0.3. The inverse tangent of 0.3 gives us an angle of 16.7 degrees. Substituting multiple independent normal and friction forces for single resultant factors drastically reduces the number of unknown variables in our equilibrium equations. Now we just need to align these resultants correctly. Let's start at the floor. The normal line here is perfectly vertical, so our first resultant force, R1, tilts exactly 16.7 degrees away from that vertical line, pushing back against the incoming wedge. Moving up to the wall, the normal line is horizontal. Our third resultant, R3, tilts 16.7 degrees away from that horizontal line, resisting the upward push of the block. Finally, we reach the interface between the block and the wedge. This is the specific point where most calculation errors occur. Unlike the floor or the wall, this surface is already angled at 10 degrees, meaning the normal line starts tilted 10 degrees off the vertical. To locate our actual resultant force, R2, we start at that tilted normal and then add our 16.7 degree friction angle on top of that. 10 degrees plus 16.7 degrees means R2 sits precisely 26.7 degrees from the vertical. Failing to add the inherent wedge angle to the friction angle is why equilibrium equations often fail to balance. You must account for the mechanical tilt of the surface itself. With our angles mapped, we isolate the 1500 Newton block. The clutter is gone. We only have three forces acting on this body: its downward weight, the wall reaction R3, and our newly calculated wedge reaction R2. Before we run the numbers, pause the video and try to write the horizontal equilibrium equation on your own using these three forces. For the block to remain stable horizontally, the leftward force must equal the rightward force. That translates to R3 times the cosine of 16.7 degrees, set equal to R2 times the sine of 26.7 degrees. From there, we substitute that horizontal relationship into our vertical equilibrium equation. The upward push of R2 supports both the downward friction of the wall and the 1500 Newton weight, allowing us to solve for exactly how much force R2 carries. Because the block and wedge share the R2 force at the interface, resolving the block's equilibrium first provides the specific magnitude needed to calculate the forces on the wedge. Now we apply that data to the wedge. Our diagram here holds three forces: the floor reaction R1, our now known interface force R2 pushing back down, and our single remaining unknown variable, the input force P. Since we have the magnitude and angle of R2, we balance the horizontal forces one last time to find the final value for P. Compare the size of our calculated input force directly against the 1500 Newton weight resting on top. That gap in size is the mechanical advantage of the wedge, using the solid floor and a shallow incline to support the majority of the load. This four-step cheat sheet outlines the entire process. First, find your friction angle. Second, merge your standard forces into single resultants. Third, calculate your tilts, adding the wedge angle for the inclined surface. Finally, solve the block first, so you have a known force to bring into the final wedge calculation. Wedge mechanics rely on this systematic reduction of variables. By condensing 6 independent forces into 3 resultants, we reveal the underlying leverage of the machine.